Welcome to another video. In this one, we'll be working a little bit backwards. We're covering chapter 6.5, nerves, hormones, and homeostasis, but we'll be starting out by talking about the physiology of neurons and then moving to the gross anatomy of the nervous system. Here's a quick sketch, you can laugh at it, of the nervous system of the body, and we'll talk about how it's organized next time. But when we typically think of the nervous system, we think of these electrical impulses that just move through. You know, you might get feeling in your toe and some signal sent back or some kind of chemical movement. And that chemical movement is really going to be the focus of what we're looking at. And we're going to start by taking a look at the functional unit of the nervous system, which is a neuron. And what you're looking at right now is a nerve cell or a neuron. And the neurons are the functional part of the nervous system. They're the cells that do the things that you typically think of, which is to conduct electrical signals. In fact, they're electrochemical signals. And a couple parts that we need to take a quick look at, although we will go back over this, so you don't need to worry about the anatomy of the neuron quite yet. Up here you have dendrites, and they're sending all the signals in exactly like I'm showing, outward, inward, to the cell body. You can recognize the cell body. It's no different than any other animal cell that we've really looked at so far. You've got a nucleus, your ER, your Golgi, mitochondria. Anyway, down at the other end, you've got the terminal end, but what's really important is this piece right here. Very, very long. The cell body, the terminal ends would look exactly like you'd expect in any other cell in terms of size. But this axon right in the middle is incredibly long. They can be feet long, which, considering it's only one cell, really, really big. Think about it. I mean, these can go from your spine down to the tips of your toes, or even your brain to the tips of your toes. So a very big piece. And when we're looking at this, it's the axon that we're most interested in. So this whole thing is the axon, and signals are always going to be passed in that direction. Always. We'll look at why that is here in a second. Okay, so let's go ahead and zoom in on the axon, because something important is happening on the axons to maintain what is called a resting potential. So we've got these sodium-potassium pumps, which is a form of active transport, and they're present all along the length of the axon, and they're maintaining resting potential. So when the pump is working, you're maintaining resting potential. Okay? So in a normal situation, what ends up happening is that the pumps are constantly pumping 2K potassium into the cell, and every time 2 potassium get pumped in, 3 sodium get pumped out. So overall, you've got a net positive charge getting pushed out of the cell. Additionally, you've got big negative organic molecules that are stuck all inside of here. So the net effect is that you've got a negative charge on the inside of the axon and a positive charge on the outside. One way I remember this, and it's kind of silly, but that you have a 2K in, so like toucan, I think I spelled that wrong. Anyway, but I just picture the word toucan, and it's 2K in to remember that it's going inward. And then you just have to remember that 3 sodiums are going out. I have no other tricks for that. But again, this is going to set you up with a resting potential that is creating an imbalance of charges, where you've got a positive charge on the outside and a negative charge on the inside. And again, negative on the inside, positive on the outside. So compare that, the resting potential, with what is called an axon potential. When you start thinking about a nerve sending that electrochemical signal down the path of the entire axon, right? We've got our axon, and again, it's sending the signal downward in this direction. The thing that's going to happen is that, and we'll start talking about how it happens later, but somehow the body of the cell sends a signal downward. Okay, and as soon as that signal gets to the part of the axon that we're looking at, some chemical changes are going to happen. So we've got these little channels, and they're referred to as voltage gated, meaning as soon as the voltage changes, remember, if we're thinking about having a positive and a negative charge on the inside and outside, that's voltage. It's just like how a battery works. So think of this as being like a little battery, and you've got these little gates or channels that are passive. They're a type of passive transport. which are going to let things flow from areas of high concentration to low concentration. So at this point, remember, we've pushed all the K in and the sodium out. And if one of these channels opens, there's going to be a flooding in one particular direction. So it turns out that the first thing that happens are sodium voltage-gated channels are going to open. So what is the net effect of this? Well, you're going to get a very, very rapid increase of the charge of the inside of the cell, because all of these sodiums are flooding in, and there's hundreds and thousands of these gates, okay? So that's starting the action potential, and we can come down here and kind of look at what that looks like. So now, instead of having sodium on the outside and potassium on the inside and having a positive charge on the outside and negative charge on the inside, this is switched a little bit because you've got sodium and potassium on the inside, and all of that's just hanging out. And now you still have a little bit of sodium on the outside. You're going to have the voltage-gated channels open up and the sodium rush in until you've reached equilibrium with the sodium. So some sodium on the outside, some on the inside, tons of potassium still on the inside, and that switches the charge. So all of a sudden, now you've got a positive charge on the inside and a negative, comparatively, on the outside, okay? That means you're in an action potential and the voltage has increased. We'll look at exactly how that looks on a chart here in a minute, but as a recap, here we go. As a recap, in a normal resting potential state, you've got your sodium-potassium pump maintaining a positive charge on the outside, negative charge on the inside by putting a little bit of potassium, which is, yes, positively charged, but again, for every 2 coming in, 3 positive charges are going out. So we've got, like I said, a net positive on the outside, negative on the inside, plus we've got these negative ions here. But then, when an action potential begins, voltage-gated channels open, and these are going to be the sodium voltage-gated channels. So sodium's going to leak in, rush in very, very quickly, and you've mixed your currents. Well, just like there's a sodium voltage-gated channel, there's also a potassium one. So then potassium, that's potassium voltage-gated channels. So potassium voltage-gated channels are going to open up. So what would you expect to happen? You've guessed it. All of this potassium is going to flood out. And again, it's going to keep flooding out until you reach equilibrium. So you've restored your, You've restored your negative on the inside and your positive on the outside. But there's a small problem, because for another action potential to come through, for another impulse or another nerve signal to move down this axon, right, it's going to have our original conditions met, where we've got sodium on the outside and potassium on the inside. That is not the case. These have reversed, and instead of having potassium where it needs to be and sodium where it needs to be, all the potassium is leaked out and all the sodium has come into the inside. Not all of it. Again, we've reached an equilibrium, but for keeping it simple, everything has switched. Okay, this is known as the refractory period, because when the part of the neuron is in this condition right here, where you've got everything inversed, a nerve signal cannot pass through. Think of it. If a nerve signal were to get here, and the voltage-gated channels that started this whole thing, right? We started with the sodium voltage-gated channels. Well, if the sodium voltage-gated channels were to open up in this part of the nerve cell, nothing would happen. I mean, it's already at equilibrium. So, in order to restore the resting potential, we've got our handy sodium-potassium pumps, and they're going to get right back to work, putting 2K in for every 3 sodiums out, and you're going to restore that correct positive and negative charge. Again, that is called the resting potential. Okay? So now we're going to look at this in a little bit of a different way. We just looked at what's happening on the axon, and now we're going to apply that to its voltage, okay? So I'm going to start by drawing a graph, very poorly drawn, I apologize. We've got time on the bottom, and the membrane potential on the side. And what that means is what is the overall charge of the inside of the cell as compared to the outside of the cell. And so we've got all of this is in millivolts, and we can go negative because if the inside of the cell is negative, then our graph is going to show it as negative. So let me start by putting that in. I'm going to pick a different color just so it's a little bit not as distracting, I guess. Okay. So right here is going to be 0 millivolts. So in resting potential, we've got a very, very negative charge on the inside of the cell. And we're right around negative 70. So at this point, we've got resting potential. After that, we have a point called threshold, which if the voltage changes enough, right, we can just kind of be hanging out around, negative 70 or so, and there's no big deal. But if all of a sudden we reach threshold, that's enough to rapidly depolarize. And we'll get all the way up to roughly positive 30 millivolts. Then there's a period of repolarization, not just down to negative 70, but past it. And then back up until we get to resting potential. And so again, I'm going to zoom in on this and look at each part individually. Down here at the negative 70, switch my pen here. Okay, so I've drawn in the threshold and the resting potential. So we're chilling somewhere around negative 70. We haven't hit our threshold. That's roughly negative 55. And during this stage, the sodium-potassium pump is working. So if we took a look at an axon, here's the inside of the axon and the outside of the axon. The conditions look like this. Let me switch back to pen. So on the inside, we've got all of our potassium. On the outside, we've got all of our sodium. Remember, we have more sodium on the outside than we have potassium on the inside. And additionally, we've got those big negatively charged organic molecules. So overall, we're looking at a negative charge on the inside and a positive charge on the outside. So that is during resting potential. The first thing to happen is at this stage right here, once we finally hit our threshold, we're going to have a rapid depolarization. And during our depolarization, this is when the sodium channels are going to open. And because of the sodium channels opening, again, we'll draw our axon. We used to have all of the sodium on the inside. No. Ignore that. We used to have all the sodium on the outside, and they're rushing in rapidly. So now we've got sodium and potassium on the inside. And again, we've got sodium on the outside, but we'll just kind of ignore that for now. And you have that depolarization, meaning that you did have a positive charge on the outside and a negative on the inside. And now it goes to being neutral and even above that to, like I said, roughly in the 35 or so range, 30, 35 millivolts in the positive direction. So the inside of the cell becomes positive and the outside becomes negative. Now we can take a look at the other side of that. We hit a point right up here, roughly plus 30, where the other voltage gated channel that plays a part of this switches. Okay, so before in this area we just have the sodium channels opening, and now in the repolarization stage you're going to have the potassium channels opening as well. And again, we can kind of draw that. So now we did have sodium and potassium on the inside. Now we've got sodium on the inside and potassium on the outside. That reestablishes a positive charge on the outside of the axon and a negative on the inside. The problem being is that we're on the wrong side. So if the sodium channels were to reopen right here, there's nothing very exciting that would happen because we've already got sodium out here. No exchange would happen. No voltage change would happen. So if we move down along here, that's what's going to bring us, so that rapid flooding out all throughout this section represents the potassium leaking back out. So down here, we're in an area called hyperpolarization. And so this is going to be the stage where everything's reversed. Instead of having the potassium on the inside and the sodium on the outside, that has been reversed. So you still do have a negative charge on the outside, positive charge on the outside, negative charge on the inside, but not in the direction that you want it to. So along this little piece right here, as we reestablish ourselves towards having a resting potential, the sodium-potassium pump fixes the gradient. And if we take a look back at all of this, hopefully you can see it's probably a little bit small on your screen, but our action potential starts all of this. Resting potential starts all of this. So we're chilling here under our threshold. The sodium-potassium pump is working. We're spending energy. Sodium-potassium pump meaning you need to be using ATP. ATP is responsible for making this whole thing happen. Constantly pumping the potassium in, sodium out. Just remember 2K in, 2K. It's all I got. You hit the critical point right here where you hit the threshold. All of a sudden, the sodium channels open. You have a rapid flooding of sodium in, causing a positive charge. Then the potassium channels open, causing the potassium to flood out. Everything is now switched in the hyperpolarization stage, and to reestablish your resting potential, you need your sodium-potassium pump to get you there. So this right here, these channels are passive. These channels are passive. They're facilitated diffusion. They're getting help, but not help with energy. It's just got a channel that's allowing things to go down the concentration gradient. So again, depolarization, repolarization, no energy input. It's only maintaining the resting potential that you're going to have to be putting in ATP.